Hello everyone, my name is Hualin Chan, and on behalf of Untitled, it's my pleasure to present the work Gradient Code Generation for AI Accelerators with specialized data layout requirements. The talk will contain 4 parts. We'll start with short introductions and followed by mathematical fundamentals of the proposed method of backward kernel generation for convolutions. After that, we will present some preliminary numerical experiments and results, and then with some conclusions. So let me start with a short introduction to the main subject of this work. It's generating effective backward kernels for convolution operators. This was present an alternative approach of generating the backward kernels, which by using the forward convolution kernel, which consists of image-to-cone operator and matrix multiplications. It's one of the most popular way that we can perform the forward convolutions. We have chosen this topic because that the convolution is one of the most popular and the most extensively optimized operator in the modern deep neural network. But when we use the image-to-cone and matrix multiplication in the forward, the backward will use also matrix multiplications and cone-to-image operator. And the cone-to-image operator is not very efficient because it performs a multi-to-one gradient operations and requires more memory access. Also, additionally, we try this approach because in Huawei DaVinci processor, we have a hardware solution implemented for further speed up the image-to-cone operations. The work and with this new approach require non-trivial data format or layout conversions on the input and the outputs. And we will present an iterator-based method to perform these data conversions. And we will illustrate the method for the data layout used in Huawei DaVinci processors. To provide the final formulas for the proposed backward kernels, let me start with basic formulas in case input tensors are in the NCHW format. So the forward, let's denote the forward operator taking the input x and the kernel k, and the result is the tensor y. The convolution operator can have the parameter as a stride, dilations, and padding. And the forward, one of the most popular way to achieve y is using image-to-cone and matrix multiplication. It means that the y equal the matrix multiplication of image-to-cone of x and k. In the backward kernel, we will receive the so-called hat, means that's the gradient of the loss value with regard to the forward y, and we need to calculate the gradient with regard to the input x and to the kernel k. The formula for the gradient kernel of the input x is shown on the slide. You can see that the dx can be calculated as a convolution of a strided hat and a flip road of the kernel. Where by strided hat, we mean that from the hat in h and w dimensions, we insert a number of zero-filled rows and columns between the rows and the column of the hat. And if the forward operator has the stride SF, the number of inserted columns between each column and rows in the head is SF minus 1. So here we have an example that the forward stride was 2. So we can see that when the forward stride is 1, the stride head is identity operator. The flip root of a tensor of the NCHW tensor, it means that we flip or we transpose the dimension n and c, and we rotate the data 100 by 1. We rotate the data in the dimension h and w. The gradient kernel for the input k also can be also calculated using convolutions, and you can see here that we transpose the dimension of the x and the head. We perform the convolutions, and the result further transpose again in the NC dimensions to achieve the gradients. So those computation scheme can be presented in the figure that we see here. Where you can see that we on the left is a forward pass, and on the right we have the 2 kernels of the backward pass. And of the 3 convolutions operator use, we denote the input channel using the red color, and the kernel channel using the kernel or the weight channel using the blue color. So we can see that in the backward pass, in order to reuse a convolution operator, we need the gradient with regard to x, and need 2 data converter, the flip root and the stride, and the gradient with regard to k requires 3 TNC data converters. This is for the NCHW format. So let me move now to the specialized data format used in DaVinci processor. So we can see that here the DaVinci processor has a requirement for convolution operator. It has a requirement for the format of the input is in a 5D format. It means that from the NCHW format, we tie the C channel by a factor of 16. We rearrange the dimension as in here. For kernel input, it is required that the kernel input is in 4D fractal format. It means that we tie both channel N and C by a factor of 16 and rearrange and regroup dimensions, as you can see here. The output, so with this format, the scheme for both channels is now updated as seen on the slide. And you can see that for the gradient of K, the 3 data converters now are not of the same type. So one of them is in TNC, transposing the NC for both for the 5D input, and the output is also 5D. But 2 of them convert, not only transpose the N and C dimensions, but it also convert the data from 5D to 4D fractal. And those data converters use computation are strongly dependent on the data layout used by the processors. So in order to describe it, we have selected the iterator-based method used in TVM to describe those converters. So in the following slides, we will show the formulas for those non-trivial converters. So on this slide is a TNC converter, which transpose in the N and C dimensions of a 5D input, and the output is also in 5D. So you can see that here both input and output have 5 iterators, and the relationship between those iterators are shown on the slide. The next converter is the TNC fract. It means that it receive a 5D input, transpose the N and see the dimension of that input, and convert the output tensor into the 4D fractal format. So as you can see here, the input printer has 5 iterators, the output has 4, and the dependency between them are shown on the slide. The next converter is a flip road, where we transpose the NC dimension and rotate in the H and W dimensions of a 4D fractal form input. And the output is also 4D fractal, and it means that both of them has 4 iterators. And here on the slide we have its dependency between those iterators. So with those computation scheme, we try to test the performance. So we started our numerical experiments with kernels for the inputs. We tested with 20 convolution shapes from the ResNet 50. At this moment, the kernels and the data converters are implemented with CPU versions. And the results are compared with the backward kernels using classical way, means that call to image and matrix multiplications. And we also compare with backward kernels auto-generated using the TVM AutoDiff module. The shapes of the convolutions are seen here and listed in the table. So here on the slide, we have the comparison of the relative execution time of the backward convolution with regard to the input versus the forward convolutions. The baseline is the time required by the forward convolutions. So you can see that we can see that among 20 cases, we have 12 cases where our proposed method have a better performance than the original one, and the automatically generated with AutoDiff is relatively not good. And for cases where we have that the proposed method is not better than the original, it is expected, because that when we can see as a breakdown here, you can see that the total time we have not for some shapes, you can see that the time required by matrix multiplication significant portions of all. So in there are places that where the time needed by the matrix multiplications override the effect given by using the image to call. So that's why there are still 8 cases. You can see that where the approach using call to image and matrix multiplication is better. But as I mentioned earlier, we know that in Huawei DaVinci processors, we have a hardware solution implemented inside the chip. You can see here that it is located in the N1 buffer between the N1 and the so-called buffer A and B. Hardware solution is to support the image to call, and averagely this speed up the time required. It speed up the performance of image to call by 5 times, by a factor of 5. With this, it changed significant. It will emphasize significantly the difference between image to call and the performance. Significantly, the performance between image to call and call to image. So with that, with that testing, when we when we taking into account the factor of 5 of image to call required in the operations, we can see that now the relative comparisons is much better for our proposed method, that our method is better than the original one in 18 cases. There are only 2 cases, that the first case and the 11 case. The 11 is not seen here because that is out of the scale, but the original is still better than our proposed method. But in 18 cases, our proposed method is better than the original one. So it shows that our proposed method is quite promising. So as a summary, you can see that with the hardware support for image to call, most of background kernel for input are faster than the version using call to image. And with the hardware support for image to call, almost we have a much better ratio of cases where the kernel generated by the proposed method is faster. So as a conclusion, so in this work we show that the backward convolution can be performed using forward convolution with data preprocessing via the data converters. And we deliver the formulas for the converters, and we tested them to demonstrate the correctness of those converters. And the iterator method was introduced to create the converters for AI accelerators with non-trivial data format requirements. And we show that our approach is able to create efficient backward kernel with respect to the input data. And but it's only the starting of our work. For future continuations, we will gather the performance for the gradients of K and the gradient regarding to the kernel. We will also gather the real performance number from Huawei AI accelerators, and we will test the proposed method with more convolution shape from other well-known deep neural networks to see that how the shapes affect the performance of the solutions. And thank you very much for your attention. And